Yes.
Okay. So you are seeing my screen?
Yes.
Yes, Professor.
Okay.
Yeah.
So as always, I make a very short review of what we studied last week. Last week we studied some things. I tell you right now. The first one we study the so-called eigenvalues and eigenvector. We we will coming back to that by the end of the course. I mean before the final exams. But however, we can do it right now or with some very small calculation. Uh, that is, suppose that we are given a matrix A of psi n by n. You are required to ask if we can find a column matrix which is a non-zero x, so that A multiplied by x will be a multiple times of x. That is by sentence, but by formula, you will have something like that. Given n by n matrix like that, it is required to find a number lambda in a non-zero columns matrix satisfying that equation. And that equation will have the name fundamental equation for eigenvalue problem. And if you can find lambda and non-zero matrix X satisfying that one, the number lambda will be called eigenvalue. And the non-zero column matrix X will be called the eigenvector corresponding to the eigenvalue lambda. And the example is here. Suppose that A to be that one and X1 and X2 to be two columns matrix like that. Then you will see X1 will be an eigenvector of A, because if you multiply A by x1, you get that thing. It is exactly 5 times of x1. So the number 5 will be the eigenvalue and x1 will be eigenvector corresponding to the number 5. Again, if we multiply A by x2, you get that thing. It is minus 1 time of x2. Then x2 is eigenvectors and minus 1 will be an eigenvalue. So that is the example. But problem is how you can find it, so that we are given an n by n matrix A. How we can find the number lambda, the eigenvalue number. And also how we can find the eigenvector x corresponding to lambda. And it is explained here. Lambda must be satisfy the equation that determinant of lambda I minus I equals 0. And that equals that formula or that equation, it has named characteristic equation of matrix A. And because last week some of students asked me why from the equation AX equal lambda x we can get that one. So I will explain it in the next slide. Here you can see. Here that is your question. So from here, how we can write it in this form. First of all, what is I? I here is identity matrix IN. It is exactly that one. We have 1 lying on the main diagonal and 0 elsewhere. And what is X? X is the columns matrix like here. X1, X2 up to Xn. Then the lambda X will be that column matrix like that one. And you remember that it is required that X is not 0, means that not on X1, X2, Xn are 0. That is a requirement for eigenvectors. Now, because In to be that, so what is it? Lambda multiplied by I. Lambda In to be that matrix on the entry lying on the main diagonal now becomes the lambda. And also 0 is everywhere except the main diagonal. And with lambda I like that, then if we take lambda I multiplied by the matrix X, we get that one. You can multiply that by what you know already. then you get lambda x1, lambda x2, lambda xn. So you see lambda x to be z1 and lambda I multiplied by x, the same reason. That is ax equal lambda x now became ax equals lambda multiplied by I multiplied by x. So whenever you have that, you can move ax from the left hand side to the right hand side, and then you get that equation. And that equation is a homogeneous system of linear equation. Because we require that eigenvector must be non-zero, means we require the system of equation has non-trivial solution. And because of that, we require that determinant of lambda I minus I equal 0. That's it. That is my explanation for the equation. And then next we study two application of determinant. The first one, that is we can use determinant to find the inverse of a square matrix. So it is here like on the screen. I recall you that the cofactor of a matrix is computed by that one, Cij to be that. And whenever you have on the cofactor, you can put them together. You can get the matrix of on cofactor. And you take the transpose of the cofactor matrix, you get a new one. And that new one has name adjoint matrix of A. Then, if A is an invertible matrix, then the inverse of A can be given by this formula. And we can write it here because A is an invertible. Then the determinant of A must be non-zero. And then we can put 1 over determinant of A. And here is an adjoint matrix we computed in the previous slide. And the example is given here. Suppose that you are given a 3 by 3 matrix like that, and they are require you to find the inverse A inverse. The first method you can apply, that is you can use the Gauss-Jordan elimination to do it, to find the A inverse. But also here you can use the cofactor, or you can use the adjoint matrix to find. In that case, the cofactor is very easy to find. But however, you need to find on nice cofactor here. And it is given in the slide here. And because of that, the cofactor matrix of A to be that one and the adjoint will be that one. Now we have enough things to find the inverse of A. A inverse equal 1 over determinant of A multiplied by the adjoint matrix. Adjoint is here. The determinant of A, you can compute it. It is 3. So A inverse will be 1/3 of that thing. And here is the final reason for you. So that example show you for 3 by 3, it is very easy to find the inverse. The second application is what we say Cramer's rule. So Cramer's rule saying if you have a system of linear equation in the matrix form like Ax equal B, and A is invertible matrix, then the system will have unique solution. This application will give you an explicit solution for the system. It is given here. Then xj will be determinant of aj over determinant of A here, where aj is obtained from A by replace the j's column by the columns of right hand side. I want to explain to you that one in Vietnamese. Cái nguyên lý Cramer nói rằng là một hệ phương trình tuyến tính như thế này. Nếu chúng ta viết ở dạng ma trận, nó có dạng ax, a nhân với x thì bằng b. Và đương nhiên là đây là số phương trình với số ẩn bằng nhau. Thế thì a sẽ là một ma trận vuông. Thì cái nguyên lý Cramer nói rằng là nếu a mà là một ma trận khả nghịch, tương đương với việc là định thức của a khác 0, thì cái hệ phương trình ax bằng b này nó sẽ có nghiệm duy nhất, Nhưng ở đây chúng ta sẽ có một cái phương pháp để là không phải chỉ nói rằng là nó có nghiệm duy nhất, mà chúng ta chỉ ra hẳn hoi cái nghiệm của nó là cái gì. Thế thì nghiệm nó được cho như sau. Trước hết là ta viết lại x là cái vector cột gồm tất cả cái ma trận cột gồm tất cả các ẩn x1, xn, và b là cái cột gồm tất cả các cái hệ số bên vế phải, ta gọi là cột vế phải. Thế thì lúc bấy giờ cái nghiệm sẽ được cho bởi công thức như thế này. Bất kỳ một nghiệm nào xg với g từ 1 đến n được cho bởi định thức của a, g chia cho định thức của a. Chúng ta chia cho định thức của a được vì a là khả nghịch cho nên định thức là khác 0. Thế còn ag là cái gì? Ag là cái ma trận nhận được từ ma trận a bằng cách thay cột thứ g, cái cột b là cột vế phải. Tôi cứ bỏ cái cột thứ g đi, xong tôi viết cái cột vế phải vào đấy thì tôi sẽ nhận được cái ma trận ag. Và nghiệm xg được cho bởi định thức ag chia cho định thức a. So that is summarized in Vietnamese, so I continue. Here is some examples for you. You can see how we can replace the right hand side column into the coefficient matrix to find the solution. Next, we begin the lecture on vector space. For the vector space, you can see that the vector we study in the high school, that is some oriented interval of straight line like that with origin and with the ending point. Then we generalize it to define what we call n space, denoted by An. That is a set of all sequence of n real number x1, x2 up to xn. And each sequence of number like that will be called a vector of n space An. Our example will be n equal 1, n equal 2, and n equal 3. That is on the geometric object we studied already in the high school. The first one, A1, is one space. Because n is 1, so here we have only one real number. And A1 will be the set of all real number. And then you can see that is nothing but the straight line of real number. In Vietnamese we say trục thực, đường thẳng thực, or something like that. For n equal 2, A2, here we call it the two space. That is the set of all order pair of real number x1 and x2. And in Vietnamese we have it like mặt phẳng tọa độ, or in English is coordinate plane. We know already from high school. Similarly, for n equals 3, we have a 3 space. That is a set of all the order triple of real number x1 and x2 and x3. Again, in Vietnamese, you have không gian 3 chiều, không gian tọa độ 3 chiều với các trục OX1, OX2, OX3 hoặc là OX, OY, OZ. That is what we know already from the high school. So is it not anything quite new for you. More than that, in An, any sequence x1, x2 up to xn can be viewed by two different ways. It can be viewed as a point, or it can be viewed as a vector. And it can be illustrated in the pictures like here. For the case n equal 2, it means on the coordinate plane, that x1, x2 is considered to be the point with the two coordinate x1 and x2. Also, it can be considered as a vector going from the origin to that, going from the origin to that one. And it has two components. The first is here, the vector, horizontal vector here. And the second is the vertical vector here. So we have two things. Then we begin define operation on vectors. Suppose that we are given two vectors u and v in the n space Rn. U and v is considered equal each other if and only if it has the corresponding coordinate equals each other. Means we have u1 equal v1, u2 equal v2, up to un equal vn. With that, we can define u plus v to be a new vector which has coordinate u1, v1, u2, v2, up to un, vn. And scalar multiplication can be defined by the formula you see on the screen. And two operations like that has named standard operation in Rn. And after that, we have the notion of negative of a vector u to be z1, and the difference between u and v to be z1. And also we have a very special vector we call the zero vector, denoted by the fat zero. That is a vector that is a sequence consisting of on zero. Then now we have a 10 property for two operations. First 5 property concerning the addition, and last 5 property concerning the scalar multiplication. And that is what we are going to borrow it to define the vector space, but in next few slides. And here are some more property for operation, and also for zero vector. And now we have an important notion, that is a linear combination. It is here. I leave it for you because today we will work with that notion. So I repeat it here for you. I will not read it sentence by sentence, just only I show you. That slide showing you for matrix we have the matrix addition, and also we have a scalar multiplication of some matrix. And now for vector we define also similar operation. And if a vector that is a sequence of number like that, we can write it in the form of a row matrix like that one, or we can write it in the form of the column matrix like that one. Then the corresponding operation are the same, will give the same reason. So first two lines, that is operation defined on vector. The next two lines, that is operation defined on the row matrices. And the last formula and the last line, that is operation defined on the columns, defined on the column matrix. And you see it gives the same reason. So we can mix them together in your exercise. Now I begin with the definition of the vector space. I said to you that we borrow 10 property. We borrow 10 property of standard operation in n space to define any vector space. Now I said a vector space is what? That is a set V, on which we define already two operations, and we call it, the name of operation is addition and scalar multiplication. And we require that two operations need to satisfy 10 axioms or 10 property listing down here. The first 5 property concerning the addition. I list it here. I list it here. And the last 5 property concerning scalar multiplication, and I list it here in 1, 2, in 6, 7, 8, 9, and 10. And as always, I call your attention to the property number 1 and number 6. We are going to use it right now. And I summarize. A vector space consists of 4 things. A vector set, a set of vectors, elements of a vector space will be called a vectors. A set of number or set of scalar and 2 operations. And it is here. I write it here. And usually a vector space can be denoted by V together with 2 operations here. Suppose that we know already the set of number is real number here. And the smallest vector space, that is 0 vector space. It consists of only 1 element, and it is exactly the 0 vector. Then we have some more example. The first example is n space. Is obviously it is a vector space because we borrow property from here to define vector space. So that is obvious that n space is a vector space. The next one is a matrix space. That is space of on m by n matrix, and here is the addition, and here is a scalar multiplication, and those are standard operation on matrix and also it will give that here is m 2 by 2, the structure of a vector space. And here is an example about the space of on polynomials of degree less than or equal n. And example number 4, that is a space of on continuous function. And there is one remark that in order to show something is not a vector space, you need to find only one axiom or one property in the definition to be broken. It is not satisfied by that. So then, and that is a way we need to show. We use to show something is not a vector space, and that is another some more property of scalar multiplication, and you can read it. That is on what we studied last week, and today we begin from this point. Now I want to show you what. Please wait for me a little. I'm open. Now it is here. So today we begin with the notion of subspace of a vector space, không gian con của một không gian vector. Suppose that we are given a vector space V. On that we have a two operation denoted by plus and fed point like that. That is two operation. Suppose that we have W. It is a non-empty subset of V, means W lying inside or equal V, and W is not empty. And suppose that if W together with the same operation here is a vector space, then W will be called a subspace of V. In Vietnamese, giả sử cho V cùng với hai phép toán như thế này là một không gian vector. V kép nằm trong V hoặc là bằng V là một tập con khác rỗng. Nếu như V kép cùng với vẫn hai cái phép toán này mà vẫn lập thành một không gian vector thì V kép được gọi là không gian vector con của V. That is in Vietnamese. So now I can explain to you. Any vector space V always has at least two subspaces. Two subspaces now is the first one is zero vector space. That is a vector space consisting of only zero vector. It is always a subspace of V. And one more thing, that is the V itself. Why that? Because here we require W is lying inside or equal V. So in case W equal V, then obviously W together with two operations here is a vector space. So V is always subspace of V and zero is always subspace of V. Two those subspace are called trivial solution, trivial subspace of any vector space V. Trivial subspace, các không gian con tầm thường của không gian V. Now, usually you are given a vector space V, and then you are given a subset W inside. You are given a W is a non-empty subset of V, and you are required to decide if W is a subspace or not. If you look at the definition, in order to verify if W is a subspace or not, you need to verify 10 properties, 1, 2, 3, 5 for addition and 5 for scalar multiplication. But however, that theorem, by theorem here I mean định lý. So that theorem claim that if you need to know W to be a subspace or not, you need to verify only two things. That is the property number 1 and property number 6, as I claim to you. That is very important for you to remember. So the theorem saying that if for U and V are in W, in the subset, it requires that U plus V is psi W. And if U is in W and C is any number, then it requires C times of U is still W1. Then the theorem claims that W is a subspace of V if and only if we need to verify only two conditions like that, nothing more. Now I give you some example of subspace that coming from the geometry, and it is easy for you to imagine. The first one is here. We consider the subspaces of R2. R2 is a coordinate plane, mặt phẳng, tọa độ. Now I list number 1 and number 3. they are trivial subspaces. The first one is a zero vector, zero sub-vector space. The last one is the space R2. And in the middle, we have one more thing. That is any line, any straight line going through the origin is always subspace of R2. And it is here. You can see the red line here. That is a straight line going through the origin. Next, we consider the subspace of R3. Again, I list the first one and the last one. That is a trivial subspace. The first one is zero subspace, and the last one is the R3. Now we have two more things. The first one is any line, any straight line going through the origin. That is absolutely like in the previous example. Now we have one more thing. The third case, that is any plane going through the origin. And by geometry, you can see it is any plane, but we require that it must going through the origin. Next, we verify.
Teacher, can I ask why it must go
okay,
to the origin?
Please ask me.
Why do we have to, to set the condition that the line in the plane have to go through the origin?
Okay. I think that I can explain to you in the break. Okay. When we take the short break, I tell you. Or otherwise, I prefer to give it to you like a homework. You can think it. You can think about that. No, I give you a hint. Please take a line which is not going through the origin. And you can verify that the property number 1 and property number 6 will be broken. And because of that, it is not a vector space. That is the reason why we always require that the line or the plane must go through the origin. Okay?
Okay, thank you.
Okay. Let me continue it. Now, I consider the set of all symmetric matrices. That is a subset of the vector space M2 by 2. M2 by 2 means the vector space consisting of all square matrices of order 2. And now we need to show that W to be a subspace of M2 by 2. How we can do it? Here. First of all, W is a subspace of M2 by 2. That is already known. And now we take A1 and A2 inside W, means that both of A1 and A2 are symmetric. They are symmetric means they equals to their transpose. A1 transpose equal A1, A2 transpose equal A2. Then if we add them together, A1 plus A2, and we take transpose, by the property of transpose, we get that equals A1 transpose plus A2 transpose. And it equals again A1 plus A2 because of that thing. And it means that A1 plus A2 is again a symmetric matrix. It means A1 plus A2 belongs to W. Next, if we take K is any real number and A is a symmetric, we have K A transpose equals K times of A transpose. And it equals K times of A because A is a transpose, A is a symmetric. So once again, we have Ka is symmetric, means it belongs to W. So because of that, we see the property number 1 and property number 6 are satisfied. So we can conclude that In that case, W is a subspace of M2 by 2. Okay, we conclude that. The next will show you the set of singular matrices is not a subspace of M2 by 2. I recall you that singular matrix means the matrix which has zero determinant. That is by definition. Now here I consider A to be that one, B to be that one, and obviously A and B, both of them have zero determinant. But however, if you add them together, A plus B, you get the identity. The identity has determinant 1. And because it has determinant 1, it does not belong to W because it is no longer a singular matrix. So it means that the property number 1 is broken. It is not satisfied by A and B. Mean that W is not a subspace of M2 by 2. That is our conclusion. The next one, again, very easy for you to imagine. The set of first quadrant vector is not a subspace of A2. That example coming from the geometry. And I call you in Vietnamese, first quadrant là góc phần tư thứ nhất ở trên mặt phẳng tọa độ. Góc phần tư thứ nhất. That is the set W is a set of all points with the coordinate x1 and x2 with non-negative coordinate. X1 is more than or equal 0. X2 is again more than or equal 0. Then it is not a subspace of A2. Why is that? You can see. If you take U with the coordinate 1, 1, obviously that belongs to the first quadrant. But however, if we take the real number -1, you multiply by U like that, you will get -1, -1. That no longer belongs to W because the coordinate is now negative, so it is no longer belongs to the first quadrant. So that we say it is not closed under scalar multiplication. The first quadrant is not closed under the scalar multiplication. In Vietnamese we say góc phần tư thứ nhất này không đóng đối với phép nhân với một số. And because of that, we say W is not a subspace of A2. And that is property number 6 is broken. So that is reason why I told you the property number 1 and property number 6 is always and is very important things. You should remember it. That one, again, something from geometry. Suppose that we are given two sets of points here in the A2. The first is a point with the coordinate x, y satisfying that. That you know already, that is a straight line. And the second one also is a straight line. We need to verify which one is a subspace, which one is not. So we can verify it by formula like that one. Let's take W to be that one. X plus 2y equals that. We can rewrite it in this form. So if we take V1 to be that, V2 to be that, you add them together, you get that one. It is still belong to W, and then we say W is closed under addition. And if we take any number K and multiply by V, you get that thing. And easily to see that is still belongs to W. So we say W is closed under scalar multiplication. Then with that, we can say W is a subspace of R2. Next, we consider W to be Z1. And there is one remark that the zero vector is not in the line. That is the remark I will explain to you later. Now, if we take V to be 1, 0, obviously V belongs to that W. And we multiply V by the number -1, you get that thing. But that number does not belong to W, means that the W is not closed under scalar multiplication, or W is not a subspace of R2. And that is by formula. But I want you to look at the geometry. You can see the example A is given by the straight line here, and that line going through the origin. And now the example B given by that thing, and that is given by the red straight line here, and it does not go through the origin. And that is why I say the zero vector is here, does not belong to the line. That is what you need to pay attention to. The next one. Now we consider the R3. Which one is a subspace and which one is not? And you can see for the first one, if you take V to be that, you multiply V by the -1, you will get that one. And that one is no longer inside W, because the last coordinate is now is -1, is not 1. So it does not belong to W. Then we say W is not subspace of R3 because W is not closed under scalar multiplication. And for the example B here, we take V to be that, U to be that, you add them together. And you can see, you can verify that it still lies inside the W. Also, K kind of V to be that, it still belongs to W. So we say, for the example B, W is a subspace of R3. And now I give you some property I will not explain in the detail. That is, it says that suppose that we have two different subspace of a vector space U. Suppose that V and W, both of them are subspace of U. Then their intersection U intersect by V is also a subspace of the big one, U here. And your homework is please verify what I write it here. Please verify by using example from the geometry of plane and space. In the previous slide, I give you a lot of examples from geometry, so you please verify that property by using those examples. Now I came to explain to you a notion somehow not so easy to follow. The spanning set and linearly independent tập sinh và độc lập tuyến tính. So now in order to define those things, first I recall you the notion of linear combination. A vector V is a linear combination of U1 up to UK if V can be written as a sum of that in this form, where C1, C2 up to CK are number or are scalars. That is notion of linear combination we studied from last week, and I remind you today in the short review. Here is some example about that. You can see that finding linear combination or something, that is kind of solving a system of linear equation. Suppose that you are given three vector v1, v2, v3 with a coordinate like that. So your example or your exercise require you to, the first one require you to prove that W with the coordinate 1, 1, 1 is a linear combination of v1, v2, v3. And the exercise B require you to show that W with the coordinate 1 minus 2, 2 is not a linear combination of v1, v2, v3. So if you remember the definition, it is very easy to do the exercise. Here I tell you, in order to prove that one is a linear combination, means that we need to find the number C1, C2, C3 satisfying that one. And we know already that W equal 1, 1, 1. And V1 to be that, and V2 to be that, and VC to be that one. So we substitute all of them inside that equation. What do you get? We get that thing. And again, we do some calculation and we get that. And from here, we get the system of linear equation like that. And we need to solve it, to solve the system here, to find the C1, C2, and C3. And and we know already that the Cramer's rule tells us that if the determinant of the coefficient matrix is non-zero, then the system is always has a solution, and it is here. And we can, if we apply Gauss-Jordan elimination, we get thing here, and that will give us the system have infinitely many solutions. It is here. And also, if you take t equal 1, you can get, for example, W equal 2 V1 minus 3 V2 plus V3. It means that W is a linear combination of V1, V2, V3. Next, if we consider that, again, W equal 1 minus 2 and 2. And once again, we substitute W in here and V1, V2, V3 from the previous slide. You get that thing. And if we apply the Gauss-Jordan elimination, you get that one. But if we look at the last line here, the last line will give us the equation 0x1 plus 0x2 plus 0x3 equal 7. That can never happen. Means the system has no solution because of that. And because we cannot find C1, C2, C3 satisfying that, we say W is not a linear combination of V1, V2, and V3. Now we go to the notion of set. Tập sinh, cái sinh bởi một tập hợp, denoted by span S. Suppose that we are given a set S of k vector inside vector space V, like that. And span of S is a set of all linear combinations of vectors in S. Or in formula, you can write here. Span of S to be that one. That is the set of all linear combination like that for any real number Ci. And the next one, the next notion, that is spanning set of a vector space. If any vector in a given vector space V can be written as a linear combination of a vector in S, then S will become the spanning set of the vectors of vector space V. And in other words, we can say S is a spanning set of V if and only if span S equal V. So because that is quite new notion for you, I will spend some time to explain to you in Vietnamese. So please excuse me for you if you a little difficult for you to understand it in Vietnamese. Sorry. Bây giờ chúng ta ở cái slide này chúng ta sẽ có hai cái khái niệm hơi khác nhau một tí. Đầu tiên, khái niệm đầu tiên là như thế này. Bây giờ chúng ta cho cái tập hợp k vector S bằng V1, V2 cho đến Vk. Thế thì người ta gọi là cái tập hợp sinh bởi S. Cái tập hợp sinh bởi S, ký hiệu là span S này. Đó là tập hợp của tất cả các tổ hợp tuyến tính của các vector nằm trong S. Và về định nghĩa bằng công thức thì nó là như thế này. Thì như vậy chúng ta nhìn thấy là một phần tử của nó sẽ là một tổ hợp tuyến tính bất kỳ nào đó của các cái anh VI, V1, V2 cho đến Vk nằm trong S như vậy. Đấy là cái tập hợp sinh bởi S. Thế còn cái dưới này thì nó có một từ khác là tập sinh của một không gian vector. Thì đấy có nghĩa là như thế nào? Có nghĩa là nếu như mọi phần tử của vector V, nếu mọi phần tử của vector V đều có thể viết được như là một tổ hợp tuyến tính của các vector trong S, thì S sẽ được gọi là tập hợp sinh. S sẽ được gọi là tập hợp sinh của vector V, của không gian vector V. Thế thì hai cái là khác nhau. Một cái là sinh bởi S, một cái là tập hợp sinh của cái không gian V. Và điều đấy xảy ra khi và chỉ khi là span S bằng V. Đấy là cái mà tôi muốn giải thích cho các bạn. So we continue with that. In case S is a spanning set of V, we can have many ways to say about that. Here are some wording of that. We can say span S equal V. We can say S span V or S generates V. We can say V is spanned by S or V is generated by S. Or we can say S is a spanning set of V. So notion of spanning set is very important things. We are going to use it in after the break. And here are some remarks. The first one, we accept that the span by empty set is zero vector. Chúng ta quy ước rằng là cái sinh bởi tập rỗng thì là không gian vector gồm có một vector không. Zero vector space is spanned by empty set. That we agree by consensus. The next one, S is always contained in span S. Very easy to verify it. The next one, if S1 and S2 are two subspace of V and S1 lying inside is a subset of F2, then the span of S1 is contained inside span of S2. Here is some examples, and after that we will take a short break. We need to show that the set S consisting of C vector like that span or generates the whole vector space R3. It means that we need to show that given any vector U inside R3, we can always write it as a linear combination of V1, V2, and V3. Means that we can always find C1, C2, C3 satisfying that one. And if we write it, because we have V1, V2, V3 is here. So we write it in the form of a system of linear equation like that. Then we need to prove that, we need to show that the system always has a solution. And because determinant of A is non-zero, determinant of the coefficient matrix of that system is non-zero. So by Cramer's rule, it always has solution, and the solution is unique. Then it has exactly one solution for any U, means S is a spanning set of R3. So that is some way to work with the spanning set. So now we take a short break and we're coming back later after 5 minutes, I suppose.
All right, Professor.
Sorry?
No, I said all right.
Okay, please ask me.
It wasn't a question. It was just I was just saying okay. That's all.
Okay. 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 So we take a short break now, please. So are you ready to come back to the class?
Yes.
Okay.
Yes.
So that one is the example we did before the break. Now I continue with that. I am going to tell you some property for the span of S. Suppose that we are given a set S of k vector v1 up to vk like that. Then the first property saying that the span S is a subspace of V. In order to verify that, you need to verify only property number 1 and property number 6. And it is easy if you remember the definition of span S. And the second one is here. If you take any subspace of V which contains S, then that subspace must contain also the span of S. It means that span of S is the smallest subspace of V, which contains S. I can explain to you that property in Vietnamese. Giả sử các bạn được cho một cái tập S gồm có k vector. Ở đoạn trước chúng ta đã định nghĩa cái tập hợp sinh bởi S, ký hiệu bởi span S. Ở đây tính chất đầu tiên nói rằng là cái span S đấy nó là một không gian con của V. Đấy là cái đầu tiên. Nó là một subspace của V. Cái tính chất thứ hai nói rằng là nó là cái không gian con nhỏ nhất của V mà chứa S. Có nghĩa là nếu các bạn lấy bất kỳ một không gian con nào khác của V mà chứa tập S thì cái không gian con đó cũng phải chứa luôn cả cái span S. So that is the true property for span S. You can remember it in doing your exercise during the tutor class. Now we continue with some more property, more notion, sorry, not property. That is linear independence and linearly dependent. Độc lập tuyến tính và phụ thuộc tuyến tính. Now, once again, we go back to the notion of linear combination. Suppose that S equal V1 up to Vk. That is a set of vectors in a vector space V. We consider an equation written by C1 V1 plus C2 V2 plus Ck Vk, like equal 0. And here C1, C2, and Ck are variable or are unknowns. We need to the equation, so we need to find the solution, means we need to find C1, C2, and Ck. And obviously, the equation has a trivial solution. It means that if we substitute C1 equals C2 equals Ck equals 0 into here, we get the equality. So the equation always has trivial solution. Then we can define if the equation has only trivial solution, always C1 equals C2 equals Ck equals 0. Then S will become linearly independent. As a case, if the equation has non-trivial solution, it means that we can find a solution which is not on Ci as 0. Then S will become linearly dependent. So that is the definition of linearly independent and linearly dependent. The definition is very easy to remember. But however, we can now we can begin with some remark. The first one, we define once again by consent that we consider the empty set is always linearly independent. We accept that notion. chúng ta quy định như vậy. And you can verify by yourself that if you have zero vector lying inside S, then the set S must be linearly dependent. Now, the case when S consisting of only one vector, then if that vector V is non-zero, then the set is linearly independent. And at this point, I can ask you one question, and then you can keep thinking about that until next few slides. In case the set S consisting of two vectors V1 and V2, so please, when that will be linearly independent? That is my question. So you can keep thinking of that. Sorry, somebody want to ask me something? Okay, so let me continue. Next, if you consider two subset S1 and S2, and suppose that S1 is contained inside S2, then we have two things. The first one, that is, if the small one, the small set S1 is linearly dependent, and the big one, the S2, is also linearly dependent. And the other thing saying that if the bigger one, the S2, is linearly independent, then the smaller one will be linearly independent. So I can explain to you that in Vietnamese. Sorry, today I speak a lot of Vietnamese sentence. Thứ nhất là tập rỗng thì chúng ta quy ước rằng là nó là độc lập tuyến tính, không có gì phải bàn. Các bạn rất dễ dàng kiểm tra được là nếu như tập hợp S mà chứa vector 0 thì tập hợp S cũng sẽ là thì sẽ luôn luôn là phụ thuộc tuyến tính. Bây giờ cái đầu tiên chúng ta nhìn tới là trường hợp tập hợp S chỉ chứa một vector V và vector V đó khác không. Thế thì khi đó tập hợp này luôn luôn là độc lập tuyến tính. Và ở chỗ này tôi có một câu hỏi cho các bạn là nếu như các bạn tự hỏi mình là nếu trường hợp S mà chứa hai vector V1 và V2 thì khi nào nó là độc lập tuyến tính? Tất nhiên là cả hai thằng phải khác không rồi, bởi vì nếu chỉ cần một thằng bằng không là nó sẽ là phụ thuộc tuyến tính ngay. I'm sorry. Please wait for me a little. So let me continue. Câu hỏi là cho các bạn là nếu trường hợp 2 thì sẽ như thế nào. Nhưng cái quan trọng hơn cái mà tôi muốn nói hơn và thực ra rất dễ hình dung. Nếu như các bạn có hai tập hợp S1 và S2, ông S1 này nhỏ hơn ông S2 thì các bạn có thể rất dễ dàng nhìn thấy là nếu cái thằng bé này S1 này mà đã là phụ thuộc tuyến tính thì cái thằng to hơn nó cũng sẽ luôn luôn là phụ thuộc tuyến tính. Và ngược lại, nếu thằng to mà đã độc lập tuyến tính thì thằng bé cũng luôn luôn là độc lập tuyến tính. Điều đấy có thể thấy rất dễ từ định nghĩa. Tôi sẽ xin phép là không nhắc lại ở đây, không giải thích ở đây, nhưng các bạn có thể làm bài tập sẽ nhìn thấy những điều đấy. So let me continue. Now, suppose that you are given three vector v1, v2, v3 like that. They are three vector inside R3, and you are required to decide if they are linearly independent or it is linearly dependent. So in order to do that, we look at the definition. Means we look at the equation like that one. And we substitute V1, V2, Vc into here. You get the homogeneous system of linear equation like that. Now we apply Gauss-Jordan elimination. We get that one. By that, it means that the system have unique solution, or we have only one solution, that is C1 equals C2 equals C3 equals 0. It means V1, V2, V3, they are linearly independent. S is a linearly independent by definition. The next one, you consider three vector like that. They are vector inside P2. So I recall that P2 is a space of on polynomial of degree 2 less than or equal to. So we consider V1, V2, V3 like that. And if we want to see they are linearly independent or linearly dependent, we need to look at the equation once again. And we substitute V1, V2, Vc to be like that. And the equation saying it equals 0 vector. 0 vector in P2 is 0 plus 0x plus 0x squared. So we get the system of equation like that. And if you solve it by using Gauss-Jordan elimination, you get that one. And that the last line of the Gauss-Jordan elimination gives us the system have infinitely many solutions. It means that the system have more than trivial solution, or in other words, V1, V2, Vc are linearly dependent. It is linearly dependent. For example, you can find C1 equal 2, C1 equal minus 1, and C3 equal 3. That is what you can see. Once again, we look at something not quite familiar to it. We consider C vector V1, V2, V3 like that in a space M2 by 2 of on vector on matrix of 2 by 2. Now we want to see if they are linearly independent or not. We write down the equation like that one. And that will become that thing. And 0 vector inside M2 by 2 is that matrix 0, 0, and 0, 0 here. So we have C1 of that plus C2 of that plus CC of that. And we get that system of linear equation. And if we solve it using Gauss-Jordan elimination, you get that one. And that one will show you the system have unique solution. It has unique solution, means it has only trivial solution, or otherwise the system is linearly independent. So that is something, some example for you to verify which one is linearly independent and which one is not. Now I give you a property of linearly dependent sets, and that will give you an answer for the question I asked you before. That is, when a system of consisting of two vectors will be linearly independent. Now we consider the set of k vector v1, v2, vk, and here we require that we have more than one vector. The set must have more than one vector, and that theorem or that observation claims that the set S is linearly dependent if and only if at least one vector inside S, say is Vj, can be written as a linearly combination of the other vector inside S. Cái tập S này sẽ là với nhiều hơn một vector, sẽ là phụ thuộc đến tính nếu chúng ta có thể chọn ra được một vector mà nó là tổ hợp tuyến tính của các vector còn lại. And it is a proof in the slide I up on the Moodle, and you can read by yourself. What I want to tell you, that is a corollary, hệ quả của nó. Corollary of that is a case when we consider the set consisting of only two vectors u and v will be linearly dependent if and only if one vector is multiple of the other vector, means u equal k of v. That is if you have two vectors, they are linearly dependent if they lying on the same straight line. You can consider it like something in the high school. Now, so please I explain it in Vietnamese. Nếu các bạn nhìn lại từ học phổ thông, trong trường hợp hai vector sẽ là phụ thuộc tuyến tính nếu như chúng có cùng phương nằm trên cùng một đường thẳng. Có thể chỉ ra hai đầu khác nhau, nó phải nằm trên cùng một đường thẳng. Vậy thì câu trả lời là nếu như hai vector mà khác không sẽ độc lập tuyến tính nếu chúng nó không có cùng phương. So in that case, u is not a multiple of the other one. So that is the answer for my question. Now I go to the notion of basis and dimension. Suppose that V is a vector space and S is a set of n vector inside V. And I suppose that S satisfies both property A and B at the same time. The first property saying that S spans V. It means that span of S equal V. And this, please forget the picture first. And the second property saying that S is linearly independent. Then, if S satisfies both property at the same time, S will become a basis for V. And what the picture means, because a vector space V can have many spanning sets, So the first round here means the set of all generating set of V. And also V can have many linearly independent sets. So the second round here means that is a set linearly independent set inside V. So what is in the middle? In the middle, that is the set which is spanning set and linearly independent at the same time. And those elements will be called basis. So that is the definition. I give you some remark. The first one, that is zero. The empty set, I'm sorry, empty, not zero. The empty set is a basis for zero vector space. And that again we agree by consent. Chúng ta quy ước là tập rỗng là cơ sở cho cái không gian vector zero. We agree that by consent. The second one, the standard basis for R3, that you know already from the high school. Now I call it for you again. I, J, and K. That is a basis for R3. I is vector with coordinate 1, 0, 0, and J has coordinate 0, 1, 0, and the last one, K, which has coordinate 0, 0, 1. That is a 3 unit vector lying on the axis in the coordinate space in the high school. And because of that, we can generalize to get the so-called standard basis for Rn. In Rn, we have the so-called standard basis consisting of E1, E2, En, with E1 equals 1, 0, 0, 0. E2 will be 0, 1, 0, 0. And the last one, En will be 0, 0, 0. And the last one will be 1. For example, if you take R4, that standard basis of R4 will consist of those 4 vectors. And next, we have a standard basis for M by N matrix space. It consists of those matrices E, E, I, J, with I going from 1 to M, J from 1 to N. And E, I, J is a matrix having entry A, I, J equal 1 and other entry are on 0. We have only one entry to be 1 and on the other is at 0. Examples, for 2 by 2 matrix space, we have 4 vectors like that. They are basis for M2 by 2. That has named standard basis for M by N matrices. Similarly, standard basis for P and X equal 1x square up to x to the n to the power n. And that one is a property of the basis. That is the property saying, suppose that V1 up to Vn is a basis for the vector space V, then any vector inside V can be written in only one way, as a linear combination of vector inside S. And that is proof in the slide I upload on the Moodle. But I want to explain to you once again what it is written here. The meaning of that is V can always be written as a linear combination like that. And if you can find another way of written it like a linear combination like that, then C1 must be equal B1, C2 must be B2, and Cn must be Bn. That is, V can be written in only one way as a linear combination of that combination of V1 up to Vn. That is very important things because we are going to use that to define the coordinate of any vector according to a given basis. We can do it the next week, not today. Now I have some property about the basis and the linear dependence. Suppose that we are given a basis for vector space V consisting of V1, V2 up to Vn. Then any subspace of V containing more than n vector is linearly dependent always. It must be linearly independent. So it is a proof here. I will not go into the detail for you. But however, sometimes you have an exercise require you to prove something to be the linearly dependent. You should remember that in order to prove something to be the linearly dependent, you need to look at the system, a homogeneous system of linear equation, and need to prove that the system have non-trivial solution. But however, by this criterion, you see that maybe you don't need to do any calculation. You need only to see the number of your considering set, the number of elements inside the considering set is more than the number of elements inside a basis. Then you can know exactly, know immediately that the set is linearly dependent. That is the meaning of that theorem. And one application of that is if you consider a homogeneous system of equation, of linear equation, if it has the number of equation is less than the number of variables, then it always has infinitely many solutions. That is one thing you can imply from the previous slide. Now I look at that thing. Suppose that a vector space V has one basis with n vector, has one basis consisting of n vector. Then any other basis of V will have the same n vector. It means that on basis for a vector space always has the same number of vectors. Always. And it is proof here, it is explained here in the slide on the button. Now we define the notion of dimension. A vector space V will become finite dimensional if we can find a basis for V consisting of a finite number of elements. If V has a basis consisting of finite number of vector of elements. So in case V is not finite dimensional, it means that in the case we cannot find a basis for V consisting of finite number of elements, then we can say V is infinite dimensional. And now is the definition of dimension. We consider only the case when V is finite dimensional. That is the first case is here. Then the dimension of V in such a case will be defined to be the number of vectors in a basis for V. And here, if V is a vector space, S is a basis for V. We denote it DIM of V, that is the dimension of V, equal the number of element inside a basis, that is the number of vector inside S. And because that is just a little complicated, it can give you some confusion. So I explain it in Vietnamese now. Một không gian vector V chúng ta sẽ gọi là hữu hạn chiều nếu như nó có một cái cơ sở gồm một số hữu hạn phần tử. Thế nếu một không gian vector V mà không thể tìm được một cái cơ sở gồm một số hữu hạn phần tử thì sẽ được gọi là không gian vô hạn chiều. Thế bây giờ với một không gian hữu hạn chiều thì chúng ta sẽ lấy ra một cơ sở bất kỳ. Ở trang trước chúng ta đã biết rằng là các cơ sở của cùng một không gian là có số phần tử như nhau. Vậy thì với không gian hữu hạn chiều như thế này thì số phần tử đấy sẽ được gọi là chiều của không gian. Và người ta ký hiệu nó bởi chữ dim V như thế này. Nó là số phần tử của các vector ở trong một cơ sở S. So you know that because in the previous slide we show that the number of vector, the number of elements inside any basis for a vector space V are always the same. So we can define the dimension of that by the number of vector space, by the number of a basis. We don't need to care about how we choose a basis. We can take any basis, it's always the same number of elements. And now we begin our example. First of all, if you consider the zero vector space, because it has a basis is empty set, means it does not have any element. It does not have any vector inside. So we consider the dimension of that equal 0. That is the first thing. The second thing, suppose that dimension of V equal n, and S is any subset of V. Then we have the following cases. If S is a generating set, it means that S will generate the whole vector space V. Then the number of elements inside S must be at least n. It means that the number of S is greater than or equal to n. And if S is a linearly independent set, then the number of S is at most n. It means it is less than or equal to n. And only when S is a basis of V, then the number of elements inside S is exactly n. That is our observation. And it is illustrated in the picture here. So I leave it for you to read by yourself. But anything is explained here. And more things, that is, if the dimension of V equal n and W is a subspace of V, then it implies that the dimension of W is at most n. It means less than or equal to n, always. And here is some example for you. The vector space Rn, that is n space. It has a standard basis consisting of E1 up to En. So the dimension is Rn. The dimension is n because that basis consisting of n vector. The next one, that is a vector space M by n. That is a vector space of on M by n matrices. We know already that it has a standard basis consisting of E, I, J, with I from 1 to M and J from 1 to N. So we count the number of the basis, the number of elements inside here is M by N. So the dimension of that equal exactly the product of M, N. And now the vector space P and X, it has a standard basis 1x squared up to x to the power n. That consisting of n plus 1 element. So the dimension is n plus 1. And the last example I want to show you, that is a vector space Px, that is a space of polynomials of any degree. Any degree, you can give it the degree 1, degree 4, or degree 1,000,000 as you like. Any degree. Then it will have a basis 1x squared x to the power n for any number n. Then that is an infinite dimensional vector space, and we say when we write the dimension of Px equal infinite, like that. Next example show you some kind of exercise. You are given two subsets like that, W to be that and W to be that. They are subset of R3, not C space R3. And suppose that we know already that both W in A and in B are subspace. Both subset W are subspace. And you are required to find the dimension of W in both cases. So how to do it? In order to find the dimension, you need to find a set of linearly independent vectors, and that set must generate the subspace. So that example is very easy to do to deal with. So I write it here for you to see. The first one, we write D C minus DC to be that thing. You see, it is a linear combination of two vectors. So if we take the two vectors here and there to put it in the set S, so S is very easy for you to see that S is linearly independent. And because of that, S is obviously span the subset W. So because of that, S is a basis for W. And the number of elements inside S is 2. So the dimension is 2. The next one is easier, I think. The 2b0, we can write it as b multiplied by 210. And if you consider the S, the set S consisting of only one vector 210. And obviously that is linearly independent and that S span W. So that is a basis for W. And because it consisting of only one vector, so the dimension is 1. The dimension is 1. Next example is here. Suppose that we consider W to be the subspace of all symmetric matrices inside M2 by 2. And what is the dimension of W? We know before the break and just at the beginning of today, we know that in our example that W is already the subspace. Then the dimension. You have something to ask me? Okay, so
No.
good. Okay, let's continue. So we want to know what is the dimension of W. We consider W to be that, and because it is symmetric, means we have B here and B there. And because of that, now we write it A, B, B, C to be A times of that one, B times of that one, and C times that one. And now is easy. We choose S consisting of C matrix like that one. And that will be spanning set for W is easy. And also you can verify that S is a linearly independent. So S will be a basis for W. And because of that, the dimension of W is 3. That is a way to find the dimension of any vector space. So next will be a way to test something to be a basis or not. Suppose that V is a vector space, and suppose that we know already the dimension is n. And if S is another set of the same number of vector like that, and if S is a linearly independent, then S must be a basis for V. So it gives you one more criteria to see if some set is a basis of a vector space or not. I claim that in your exercise many times you are required to verify if something to be a basis or not. To verify something to be a basis, you can do by using the definition. You should show that the set is a spanning set and also the set is a linearly independent. But however, here is much easier for you. Suppose that you know already the dimension of the vector space is n, and the number of vector in your considering set also the n. So you need only to verify if the set is a linearly independent or not. If it is a linearly independent, then you can know exactly that the set is a basis. And the next one again, suppose that you have the set of exactly n vector like that. And if you know that, you can verify that S is a spanning set of V. Or in other words, S generates V. Then S will be a basis for V. And it is, once again, it is illustrated in this picture. And that is the end of the section about the basis and the dimension. And our class will stop today here. And if you have some question, please ask me, or otherwise we can see next week. Please.
Teacher?
Yes, please.
When will be our midterm test?
I suppose that it will be in 2 or 3 weeks from now.
Okay, thank you.
And some more question, please. So I have
Professor,
please.
This lesson today can be in midterm test or not?
What? Yeah, I don't understand. What do you mean?
This lesson today can be is lesson today be in midterm test?
Let me explain to you for the midterm exams. For the midterm exam, you will have exercise which you have trained during the tutor class. So if something have not yet trained in the during the tutor class, it will not be appear in the midterm exam. Okay.
All right, thank you.
Okay. Something else, please.
I'm sorry. Can you hear me?
Yes.
I want to ask if we are allowed to use calculator in our exam.
You know, in general, it is forbidden. It is forbidden. But however, you know that because we are working online now, so even you can use it. We don't know. But however, my advice that please don't use your calculator because it will not help you. It will not help you in doing your computation. In doing your computation, you need to understand what I explained during the lecture. Without that, it is very, very difficult for you to do the exercise because what I require you in doing the exercise, in doing the exam, that is, you need to understand the notion, you need to understand the lecture and any definition you need, and you need to understand what the exercise require you to do. That is the most important thing. Okay, is it answer your question? Hi, please. Is it? Are you?
Well, perhaps I'll figure it out.
Okay. Okay.
Teacher, I'm sorry. Will we have a syllabus for the midterm test? Đề Cương, will have a syllabus for midterm test?
No.
Okay.
No. No, we have only the syllabus for the course, the whole course. We don't have the syllabus. We don't have a summary for the midterm. I promise to you that if we have time, I will do a revision of the whole class, whole the lecture before the final exam for you. If we have time, I don't know if we have enough time to finish the course. But however, if we finish just a little earlier than 12 weeks, then I can do the finance revision for you. Okay.
Okay. Thank you, Professor.
Okay. So
Professor,
yes, please answer me. Please ask me.
what form of the test we take? Like, is this a multiple choice, or we have to do exercise like directly on paper and?
No. You don't have the kind of multiple choice. No, that is not the way we do with the linear algebra. No.
So we have to write it on paper and take a picture and send it.
Something like that.
Yeah. Okay. Thank you, Professor.
Any more question?
I have a question.
Please.
When the midterm test start?
What?
Khi nào midterm bắt đầu?
That I answer already. Some of you asked already, and I say to you already. In 2 or 3 weeks. Not yet decided, but in 2 or 3 weeks from now. Ok. Trong vòng 2 hoặc 3 tuần nữa. Một bạn trước đây đã hỏi rồi, tôi đã trả lời xong rồi. Anything else? Okay, if no, so goodbye to all of you and see you next week.
Goodbye, Professor.
Professor.
Goodbye, Professor.
Professor.
Goodbye.